Influence line and surface analysis is an extension of the moving load analysis, which uses the effects of a unit load to rapidly compute the effects of arbitrary, complex load patterns on design lanes. Often necessary to comply with bridge design codes such as AASHTO LRFD, influence-based results find the worst-case scenario out of more possibilities than can be analyzed individually. In Larsa 4D, both influence lines and influence surfaces are supported. When girders are represented by linear elements, influence lines are used, whereas influence surfaces are used on models with a deck surface modeled as plate elements. In this section, we'll use influence line analysis to find the worst-case truck positioning according to AASHTO LRFD. There are two parts to influence line analysis. The first part sets unit loads on the bridge to compute the set of influence coefficients. The second part of this analysis places vehicle and uniform load options according to a specific design code. In Larsa 4D, a lane is a linear path in the model along which a vehicle pattern or unit load will march in a moving load or live load analysis, which can take any path through 3D space. If the lane is not directly over the girder centroid, Larsa 4D will generate the appropriate moments automatically. For an influence line analysis, we must place a lane on the structure where a traffic lane will fall. In this tutorial, because our model cross-section is 24 feet wide, two 12-foot lanes will fit. One 6 feet offset to the left on the positive Y side, and one 6 feet offset on the negative Y side. To begin generating the right lane, we'll create a new lane by opening the Draw menu, then clicking on the From Selected Members option to select Lane Surface. A new lane is now created riding on top of the cross-section surface, which appears as a line above the member elements. If you do not see the dashed line indicating the lane, you can open the Graphics menu and click Show to make sure that Lanes Surfaces is turned on. Now go to the Model Data Explorer by the Model button above the Explorers and open the drop-down menu in the Explorer to select Lanes Surfaces. Right-click the new lane and rename it Right Lane. Now we need to offset the right lane by 6 feet in the global negative Y direction. The lane path is defined relative to the members the load is applied to, and offsets will be specified in local member directions, so global negative Y corresponds to member positive Z. As per the initial choices in this tutorial, the lane path is specified in inches units, so the offset will be 72 inches in the positive Z direction, as you may recall from the display of the cross-section in Larsa's Section Composer tool. Once we right-click the right lane in the Model Data Explorer and select Edit Path and View, a spreadsheet window will open for the lane path, along with a special lane graphics view which will open on the lower half of the screen. Each row in the path geometry spreadsheet specifies a control point on the lane path, which in this case is made up of straight line segments between the control points. Click on the title of the Offset Z column, and in the menu text bar above, type 72, then hit Enter, which changes the Offset Z column to 72 for all rows. To comply with the part of the two-truck loading specification that says each truck must be on a different path, we'll tell Larsa where the break is between the spans using a span break marker. Each row in the path spreadsheet represents a geometry control point in 3D space. The row for Member 2 creates a geometry control point at the start of Member 2, which is located at the pier. We'll now add a span break marker in the next row, which indicates that the previous geometry control point ends a span. Select Reference Object or Range 12 in the spreadsheet and use the Insert Row tool in the toolbar above to add the new row. Change the point type of this row to span mark, and note that the span mark immediately follows the geometry point at the start of member 2 in row 11. Now close the spreadsheet, and we'll see the right lane is now created. To create the left lane, we'll duplicate the first lane definition and shift it 12 feet to the left. To do this, right-click the right lane in the Model Data Explorer and select Duplicate. Now right-click the new duplicated lane and rename it Left Lane. We'll now open the Edit Path and View option once more by right-clicking the left lane and then change the Offset Z field to -72 for all rows, and then close the spreadsheet. The load case setup in Larsa 4D specifies additional options for how the lane is loaded, including the grid spacing of influence coefficients. In the Load Cases Explorer, add a new load case and name it Influence Line Right. Now double-click the new load case to open the spreadsheets for the load. Select the Moving Loads tab and then click on the Influence Load sub-tab. Add a new row to this spreadsheet, then change the lane surface cell of this new row to Right Lane. In the forward increment cell of this row, change the value to 2 feet. Now repeat this process to create an Influence Line Left load case by adding a new load case named Influence Line Left. We'll open the Moving Load spreadsheet to select the Influence Load subtab, this time choosing the left lane, which we will again set to 2 feet in the forward increment cell. At this point, we're now ready to run a moving load analysis, which is selected from the Analysis menu. Being there are no options for this analysis, we can simply click Analyze and save the project when prompted. During the analysis, influence coefficients are being created for each of the lanes using 2-foot increments. Remember that we have not yet entered any information about the vehicles that will be placed on the lanes. Once this analysis completes successfully, you can close the analysis window. Although the influence solver can be used for many design specifications, the influence analysis in Larsa 4D was developed with AASHTO LRFD and AASHTO LFD in mind. In this example, we'll use AASHTO LRFD vehicle definitions which must be imported into the project from a database of vehicles provided within Larsa 4D. From the Input Data menu, select Connect Databases and choose Connect Standard Database. Open the file ashtovehiclepatterns.dml and click OK. In this model, each lane will be configured separately. For each lane, we'll create an influence line result case which specifies how to perform AASHTO LRFD live load. Under the Results menu, click Influence Line Surface Case to start configuring a new influence-based result case. On the top of the window, make sure Influence Line Right is selected. All of the default options on the first tab of this window are correct, and let's note that the load for extreme force effects is turned on. Now select the Vehicular Loading tab and click Add Lane Type. In the Select Pattern drop-down menu to the right, choose HL93 HS20-44 Design Truck. Now we'll enter the specification for the tandem condition by clicking Add Lane Type again, and this time setting the vehicle for this lane to HL93 Design Tandem. A lane type refers to the way the design lane may be loaded. In Larsa 4D, the influence line solver will choose the lane type that produces the most extreme effects. Click Add Lane Type a third time and set the first vehicle for this lane to HL93 HS20-44 Design Truck, then set the force factor to 0.9. Now click Add Vehicle, and a second HL93 HS20-44 Design Truck with the same factor is added into this lane type. Set the UDL factor on this vehicle to 0.9, which applies to the current lane type, and I'd also like to mention that we have not yet seen the UDL magnitude. Set the minimum back to front spacing to 50 feet, and turn on the option One Load Pattern Per Span, which pertains to the two-truck lane type, in which the two trucks must be placed on different spans. The span break markers inserted into the lane path definition control what Larsa 4D knows to be the spans. Select the Uniform Patch Loading tab and enter 0.64 under the load magnitude, then change the result case name to Right Lane and click OK. Now we'll repeat this process for the left lane by going back to the Results menu to choose Influence Line Surface Case, making sure Influence Line Left is chosen at the top of the window. We'll open the Vehicular Loading tab and add the HL93 HS20-44 Design Truck, followed by the tandem condition for the same vehicle load pattern. Now add another HL93 HS20-44 Design Truck with a force factor of 0.9, along with the second HL93 HS20-44 vehicle load pattern, which has a UDL factor of 0.9 with a minimum back to front spacing of 50 feet. Now turn on the One Load Pattern Per Span option. Select the Uniform Patch Loading tab to set the load magnitude to 0.64, set the result case name to Left Lane, and we can now close the window. To access results, you can click the name of the case and use the graphical or spreadsheet results. While each individual case does not provide the final values necessary for AASHTO LRFD, they are the first step. To better view the results in this part of the tutorial, let's first make sure that the simple rendering is turned on within the Graphics menu. Now in the Analysis Results Explorer, select the first influence case we made, which is the right lane. Turn on the Graphical Member Force Diagrams under the Results menu and change the report to moment MZ in the first drop-down menu of the new toolbar we see here. This graph represents the envelope of forces for all possible positions of the truck, tandem, or two-truck plus lane load, including variable axle spacing. Accessing results in the spreadsheets works as usual, except you must choose an envelope column. Under the Results menu, select Spreadsheets, Members, and then Forces Local. In this case, we'll choose to envelope on the MZ column. The rows of the spreadsheet then show the minimum and maximum MZ values for each station along the girder, plus corresponding forces in other directions. MZ refers to Member Local Coordinate System directions. You may check where Larsa 4D decided to place the truck and lane load to produce the extreme effect for any point on the structure using several methods. The first method is to look at the result case column on the spreadsheet. It indicates the station number in coordinate units from the start of the lane at which each vehicle is placed, referring to the front of the vehicle. It's also possible to right-click a row in an influence analysis spreadsheet and use either the Create Input Load case or create result case commands to create a new case that contains the loading configuration that produced the effect shown in the selected row. Creating an input load case creates a new load case with member or plate loads for the vehicle axles and UDL. Creating a result case makes a new linear result combination out of the already analyzed unit load result cases. It's then possible to either inspect a new case or reanalyze an input load case to obtain the static result for the loading configuration. The graphical influence coefficient view is the recommended method to inspect the loading configuration that maximizes a result somewhere on the structure. Select the Influence Coefficients button on the Floating Graphical Result Options tool window. Once this tool is on, Larsa 4D is waiting for you to choose a location on the structure to maximize the forces at. You can click any member to see influence coefficients for it, and be sure the pointer tool is activated. When prompted, you'll enter a station number for where you would like to see the coefficients. The stations range from 0 to the number of stations configured to be drawn graphically. Enter 0 to see the coefficients at the start of the member, and then hit OK. The graphics window will now update to show the influence coefficients and the locations of axles at their worst position. Arrows indicate the locations of the axles of the vehicle specified by the active result case that produced the maximum moment at the chosen location. You can switch between placing the axles at the maximum and minimum location in the graphical results option window. We can now turn off the graphical results through the results menu by selecting graphical and then none. In order to compute the effects on the structure for AASHTO LRFD, we need to combine the effects of the left and right lanes. Because we have multiple presence factors, there are 3 cases to consider. The right lane may be loaded individually with the multiple presence factor of 1.2. Similarly, for the left lane, or the 2 lanes may be loaded simultaneously with a multiple presence factor of 1.0. For this example, we'll create the simultaneous loading condition first, in which a linear result combination simply sums the numerical results of 2 or more cases. Under the Results menu, choose Linear Combination. Now add 2 influence line cases, one for the left lane and one for the right lane, into the list on the right, then click OK. Select the new linear combination case in the Analysis Results Explorer, and then open a results spreadsheet to view the combined effect from the 2 lanes. This spreadsheet now shows the case where the left lane and the right lane are both loaded together. Each lane chooses its vehicle type and position independently. Enveloping the 3 conditions, left, right, and together, can be done using the extreme effect groups, which are like saved envelopes. Under the Results menu, open the Group for Extreme Effect tool. Find the 3 cases for the right lane, the left lane, and the new linear result combination, and add them onto the list on the right using the arrows in the middle of the window. Set the factors on each as appropriate, and then hit OK. You'll find the new groups in the Analysis Results Explorer in a new section called Extreme Effect Groups. You can access the results for these cases like any other case, and use the result spreadsheets with these cases to find the controlling effects on each lane. Envelopes must be used when you open results spreadsheets. If we choose moment X, we can see the result case column indicates which of the 3 loading conditions was the controlling condition used for maximizing moment X at each station. In the next part of this tutorial, We'll create a basic setup for staged construction using construction and loading activities, and then compute the state of the structure after each construction step using a staged construction analysis.